Hello everyone. Today I'd like to talk about the second law of learning and its older cousin, the second law of thermodynamics, which is nevertheless very closely connected to the second law of learning. Now, those concepts are also connected to the something which is known the error of time problem, which we'll discuss, and Boltzmann brains problem that we'll discuss later. Now, the second law of thermodynamics basically tells us that the entropy of a closed system must not decrease. So it's either increases, which is usually happening in particular for physical systems, and then once it reaches a thermal equilibrium, the state of the maximum entropy, it stops increasing. So this is the usual interpretation of the second law. Now, one important note that I'd like to make is that it is a completely classical concept, and nevertheless it breaks the known symmetry of classical systems. Usually, if you have a classical system, and if you look at some solution of a classical system and then you run it backwards in time, it is also a legitimate solution. It's a possible solution of the system. And so in this sense, classical physics is completely time symmetric, and yet the second law of thermodynamics breaks this symmetry. Now, the standard explanation why the symmetry is broken, why does it seem that there is a order of states starting from low entropy to going larger and larger entropy states, is because the universe must have started in a very low entropy state. This is the usual interpretation. Now, physicists work hard trying to come up with a theory that would give you initial state, low entropy initial states, and one of the best candidates for that is so-called cosmic inflation. Now, of course, what will happen eventually if you just look at the system from the Big Bang on, so yes, it starts with a very low entropy state. Now the entropy keeps growing until it reaches its maximal entropy state, like a thermal bath. Now, at that point, what will happen is that from time to time, due to thermal fluctuation, observers would form out of nothing, right? So out of this thermal bath. And this is known as Boltzmann brains. So basically the idea is that a brain which hallucinating, having memories, would just come into existence, and once it comes to the existence, it may have memory just like the memories we have now. So living on planet Earth, maybe listening to this podcast. And the prediction of what should happen with such a system, with such an observer, is that in the next split second, it should just disintegrate, right? And without even leaving any trace. So that's the prediction. Now, of course, this comes naturally from the classical physics, where entropy was first low, then it went high, and then there is this heat bath. Now, you may think whether this bizarre prediction can be changed if you include quantum mechanics, and quantum mechanics does add an interesting twist to the problem, but it doesn't resolve this problem of Boltzmann brains, of the conclusion that you would be expected to be a Boltzmann brain. Now, so that's what quantum and classical physics are saying. Now let's see if neural physics can put something new into the picture. So the entire universe is actually a learning system made out of the fundamental neurons, similar to biological neural networks. Would that save the day? Well, indeed, as we well know, and we experience all the time as biological organisms, that there is some kind of a symmetry in time, right? We remember the past, we don't seem to remember the future. At least most of us don't remember the future, don't know the future. And so in this sense, the symmetry is broken in the biological systems that we know, like us. Right? So, and this phenomenon of breaking a symmetry, of not remembering the past, but not remembering the future, but remembering the past, is known as the error of time. Now, it's also, there's something else interesting happens with biological systems. They do seem to be always in the lower entropy state, and so they prefer more organized and low entropy states. And in this sense, it's kind of already working in the opposite direction from the second law of thermodynamics. And so maybe if we dig deeper and trying to understand what is different for the biological system, we may see why the conclusion of Boltzmann brains may be avoided. So basically the idea that I'd like to discuss is maybe, the second law of thermodynamics as we know and like it isn't as general and as universal as we might have thought. Maybe after all it doesn't apply to all systems, or it doesn't model all systems well enough, and maybe it should somehow be generalized. Now, before we go into that direction, let's just look at the usual arguments of how people try to avoid contradictions with the second law of thermodynamics when dealing with biological system. So usually the argument would go, well, biological system is an open system, and since it is open system, it is interacting with the environment because it's open system, and so the second law may not necessarily apply. Now, of course, this is a correct argument. Yes, strictly speaking, it only works for the closed system. But then, if we start considering the entire universe is the only system for which the second law applies, then we encounter the very same problem we discussed in the beginning, the Boltzmann brain problem. Now, moreover, this second law of thermodynamics becomes almost completely useless, right? So if you can only apply it to the entire universe and you cannot really apply it to subsystems, then it's not really useful in a laboratory. So perhaps the correct approach here is that, it's true that sometimes entropy can increase, sometimes decrease, but the question is, what determines? If I look at a subsystem, and how do I decide whether the entropy of this subsystem should increase or decrease? Can there be something in this neural physics, when we're modeling the entire universe as a neural network, can there be something that would help us to identify the criteria that would determine whether whether the entropy of a system should grow or not? Okay, so now recall that in the context of the neural physics, where everything is made up of these fundamental neurons, there are typically two types of degrees of freedom, and this is actually an important point of this approach. Now, the one type and the two types of processes that govern the evolution of those two types of degrees of freedom. Now, the first one is the so-called activation dynamics, and it is describe the evolution of the non-trainable variables. And this one is very much familiar to us from physics. Basically, if there is a state of some degrees of freedom, and there is some rule according to which this state evolves, then we can just evolve it forward in time and see how the state changes. And this is pretty much how classical physics and also quantum physics works. In classical physics, you describe a state in the phase space, and then Hamiltonian equations of motion describe you how it evolves. In quantum physics, you have a state in a Hilbert space, and then you have Schrödinger equation describing how it evolves. Okay, so we have all that, but what else comes with neural physics is the second type of degrees of freedom and second type of process that is completely unfamiliar to us, to the physicists. Basically, it is the trainable variables and the learning dynamics that describes how those variables evolve. Now, we don't usually build theories by incorporating some kind of learning into them. This is not how we develop physical theories. Now, however, there are some preliminary results that suggest that maybe a gravitational system is of this kind, and we do see some features of learning in the gravitational system. But this is definitely beyond the discussion of today, and so I'll put the gravitational physics aside. Now, coming back to the problem of the second law, and now that we know that there's these two types of dynamics, the activation dynamics and the learning dynamics, can it actually help us to solve the problem of Boltzmann brains? Does it bring something new to the table so that we can actually make sense of the fact that the different subsystems in the universe can have both, either increasing of the entropy or decreasing of the entropy. Well, what happens actually in theory of learning, for example, in a machine learning system, that the learning system is trying to basically adjust its parameters to model the data set, like in a machine learning system, or biological learning system trying to adjust its trainable parameters to model the universe around it. And by doing that, it basically is recording information about the environment in its own trainable variables. And by doing that, it is decreasing the entropy. So it's basically the tendency of a learning system is to reduce the entropy. Now, and that is exactly the opposite of what the activation dynamics does, or usual physical dynamics that we used in physics does, where the entropy usually goes up. So basically, that means that there are these two competing processes, and we may be able to use them to generalize the second law of thermodynamics. Basically, we would say, well, yes, there is activation dynamics, and as we are used to in physics, due to this dynamics, entropy goes up, and so the second law of thermodynamics holds. But there are also learning dynamics which can allow the entropy go down. And so this is a more general law, second law of learning, that would tell you that either of those two effects can dominate. So for example, if you have some subsystem where the activation dynamics dominates and there is not much learning for whatever reason, then this subsystem is expected to behave as the usual physical system for which entropy grows. Another way around, if you have some subsystem for which the learning dynamics dominates, then we would expect for that subsystem the entropy to actually decrease. And so then we would be dealing with exactly these two competing phenomena, and different subsystems would behave differently according to which kind of degrees of freedom or what kind of dynamics actually dominates for them. Now let's take an example. So let's take a very small learning subsystem, maybe an atom or a molecule. For that subsystem, it is small, so it would take very little time to be trained and to get to the state of probably local equilibrium. So at this point, the entropy would stop decreasing, and such a system we expect to behave as a normal physical system for which entropy can only grow. Now, on the other hand, if we have a more complex system, maybe a cell or an organism that has many more trainable degrees of freedom, then that system can potentially continue training itself, learning the environment, and as a result of that, its entropy can go down. And so as long as we are concentrating on the time scale where the learning equilibrium wasn't reached for that larger system, we should be seeing the violation of the second law of thermodynamics, which would agree with this generalized law, the second law of learning. Now, one may also wonder how to describe, let's say, a transition from a state where you only had activation dynamics dominating systems like molecules to another state where the learning dynamics dominates, right? So you would have maybe a collection of molecules, ensemble of molecules, and then it transitioned to ensemble of maybe organisms. So all this is, of course, a very interesting questions to discuss, and we'll definitely get back to that. But and moreover, it would be interesting to see if you can actually recreate such a phase transition in the lab, and if you could, maybe we can learn more about when the system can make this phase transition from maybe non-living to a living system. And of course, all this, and there are many other related questions that one can ask in this context. But that is all I wanted to talk about now, just the second law of learning, and then perhaps some other time we'll discuss the origin of life and the phase transition associated with the origin of life as a direct consequences of the type of the second law of learning. Well, that's all I had to say. So thank you for listening, and I'll see you next week. Bye bye.